The objective of this video is to populate the single-pole double-throw converter with real semiconductors. So we're going to be talking about how you go from a single-pole double-throw converter in an idealized sense to actually building it with real MOSFETs and diodes. And in order to decide how to do this, you need to characterize your converter in terms of whether the throw voltage is always positive, always negative, or whether it can be AC, and whether the pole current is always positive, negative, or whether it can be AC. So with this in mind, we can draw a map of the possible combinations of pole voltage and throw current. In our map, or our chart, we can label the y-axis as the polarity of our pole current, so the top is positive current, the bottom is a negative current. And our x-axis can be the polarity of our throw voltage. So VT positive on the right, or on the east side, and VT negative on the left or on the west side. Let's start by considering the northeast quadrant, where we have a positive pole current and a positive throw voltage. We can realize this single-pole double-throw switch as a combination of a MOSFET, or a transistor, and a diode. Now I keep saying MOSFET. Technically this could be any transistor. Back 30 years ago or so, this would have been a BJT, but these days it's typically a MOSFET or an IGBT. So I've drawn a symbol in this circuit of a MOSFET, and as drawn here, we've got the drain on the top and the source on the bottom, and the MOSFET can block a voltage like this, VDS. It's not able to block a voltage in the other direction. So you can see it's critical that this arrangement of the MOSFET and the diode appears in the top right quadrant, where we're applying a positive throw voltage across the chain of the MOSFET and the diode. The next thing to point out is that we can reverse engineer the current path. So we've said that in this case our pole current is always positive, and so our current is either going to take this path here through the diode, or it's going to take this path here through the MOSFET. Let's contrast this to the case where our pole current is negative. In that case, we'd have the following realization. So here I've labeled the arrow for IP in the same direction, but actually our current is taking a path into our switch like this, because it's in the negative direction. So you can see that now the arrow in our diode and the arrow in our MOSFET point in the path that the current is going to take. So it's either going to flow up through the diode, or it's going to flow down through the MOSFET, based on whether we have the MOSFET gate on or off. So this is a memorization trick for how you can remember the configuration of your MOSFET and your diode. You can look at the direction of the arrow on the devices. It has to match the direction of your pole current. If your pole current is always positive, as was the top case, where it comes out of the pole, then your diode and your MOSFET must allow the current to travel that way. If you were to reverse the direction of this diode, it simply would not work. We can complete this by drawing the other quadrants. I'm not going to talk about this in detail. You can refer to your lecture notes for those quadrants. And in this case, the throw voltage is negative. So this is a map of the different realizations. Let's now zoom in on this case down here and talk in detail about how this works. So when you have unidirectional current flow, you can realize this as a transistor-diode pair, which are complementary. What does complementary mean? It means that one device is on, when one device is on, the other device is off, and vice versa. Well, how does this work? How is it that we can realize a switch that can be connected to either throw 1 or throw 2 with only a single device that's active, that is the transistor, while the other device is passive? As I said before, this relies on unidirectional current flow. And it also requires the current to be stiff. We've talked in previous lectures about the use of inductors and capacitors to stiffen our voltage and our current. This principle, this ability to use a transistor-diode pair, requires a stiff current source on your pole. So here we've labeled IP as going out of the pole, but we've attached it to a negative current source. When our MOSFET is conducting, when our MOSFET's turned on, we effectively have a short across the MOSFET, and our current takes this path here. We can see that at this instant of time, our entire throw voltage, our entire value of our capacitor, is applied across the combination of the MOSFET and the diode, and since the MOSFET is a short circuit, it has 0 volts across it, and so that voltage has to appear across the diode. When our MOSFET is turned off, the current has to continue to flow since we've hooked it up to a current source. So the current will actually force this diode on and take a path like this. By forcing the diode on, we now have only the voltage drop of the diode, which is approximately 1 volt, appearing here, and the rest of the throw voltage has to appear across our MOSFET. That would be Vt minus 1 volt. So you can see in this configuration that we've relied on the stiff current source in order to enable us to realize this complementary transistor-diode pair. If our current source wasn't stiff, we simply wouldn't turn the diode on. The other thing to notice is how much we depend on the polarity of the devices. That's to say that the map that we drew earlier is unique and specific to the quadrants that each switch and diode configuration is labeled. So consider, for example, in our circuit here, that we reverse the direction of the diode. Let's say that we draw our diode like this. In this situation, when our transistor turns on, we're going to have the entire forward voltage of our throw across the diode, and the diode cannot block voltage, so we're effectively going to have a short circuit across our throw capacitor or our bus capacitor. This will cause an explosion. Another thing that will happen is, suppose that we now have our transistor off, but we've hooked it up to this current source, right? The current has no path to flow. The current cannot go this way because the transistor is off, and it cannot go this way because the diode is blocking it. This will also cause a device failure. And similarly, we can talk about the importance of the polarity of the transistor. So in this case, the transistor is able to block a voltage from drain to source. If you reversed the polarity of the transistor, now you'd be unable to block your throw voltage. Next, let's consider the case where we have bidirectional current. What if we want to realize a single pole double throw switch when our current is AC, but our voltage is DC, our voltage is unidirectional? So this corresponds to the northeast and southeast quadrants. We have the following switch realization. So our current can take either direction. Let's draw the paths of this. So if the current is currently heading out of the pole, the current will either travel like this when the bottom diode is conducting, or like this when the top MOSFET is conducting. If the current is currently going into the pole, it will take a path like this when the top diode conducts, or a path like this when the bottom MOSFET conducts. So you can see we've effectively created a parallel arrangement of devices to allow the current path to flow in either direction, but we retain our ability to block the throw voltage. Let's now consider the case where we have an AC throw voltage but a DC pole current, or in other words, an AC throw voltage and a unidirectional pole current. So clearly we again have two current paths, either through the top transistor and diode or through the bottom transistor and diode. The diodes are again pointed in the direction that we want to be able to draw our currents, but they provide protection for the MOSFET so they can block the AC throw voltage. So this diode can block a voltage like this, while this MOSFET can block a voltage like this. And similarly on the bottom. The final case is the ultimate generalization. This is a four-quadrant switch, which allows us to create semiconductors that behave like our complete mechanical single-pole double-throw switch. So in this case, our throw voltage is AC and our pole current is AC. And we can view this as taking our previously drawn bidirectional switch and putting it in parallel with a switch configuration that allows current to take the opposite direction. So you see right now we've taken this diagram and we've sketched it over here, and now we will put a diagram in parallel with it that allows current to flow in the opposite direction. And again, with some effort we can reconstruct our current paths and identify that we were able to block this bidirectional throw voltage. So finally, I want to remark that you don't actually have to memorize these configurations. You can take the observations that we've made here, the ability to block voltage and the ability to have a current path in all situations, and construct the diode and MOSFET combination that will allow you to realize the switch.